Now it's time to look at linear least squares, at least make a formal statement of the problem. We're given a matrix A, which is n by m, and a vector B, which is n by 1. The task is to look over all choices of m by 1 vectors x and minimize the mismatch between ax and b. In other words, pick x in Rm to make ax as much like b as possible. Mathematically, this is expressed as minimize over all m by 1 vectors x the norm of the difference or mismatch between ax and b. That's the least squares problem. Now, if several different m by 1 vectors x achieve the same minimum mismatch, then among them choose the smallest such x. And smallest can be characterized in many ways. Two ways that we'll address are the smallest in norm or the smallest number of non-zero entries. These are different, and we'll see that via examples. Notice that this problem formulation really generalizes the problem of solve ax equals b. This says make ax as close to b as possible. If the mismatch can be made 0, then we've solved the ax equals b problem. If the mismatch can't be made 0, minimize the mismatch. Make it as small as possible in the sense of the norm of the mismatch. And then if that can be done many ways, choose the x itself, which is the smallest. This linear least squares problem generalizes the problem of linear systems of equations. We're going to mostly focus on this top aspect, doing the minimization, finding an x that minimizes the difference ax minus b. The second part below, which addresses the situation when many different vectors achieve the same minimum, well, we'll talk about that and see the tools in MATLAB to solve that, but we won't be able to go over the theory of how that's done. I'll leave that for another course as you move through your education and pursue possible interests in these types of numerical questions. Now let's look at this norm minimization a little bit further. Suppose that the value of a function f is always non-negative, so f is greater than or equal to 0 for all values of x. Let's define a function g as the square of f. Simply, g of x is f of x squared, or f of x times f of x. Now, the function which squares its argument is monotonically increasing on non-negative values. There I've shown sigma squared versus sigma, and notice that it's monotonically increasing while sigma is positive. That shows that if we choose x to minimize f, it's really the same as choosing x to minimize f squared, or g. So with that in mind, our least squares problem, choose x to minimize the norm of ax minus b, can be thought of as choose x to minimize the square of the norm of ax minus b. Any x which minimizes the right-hand side here will also minimize the left-hand side here, because the function which squares its argument is monotonically increasing. Let's write out what the norm of ax minus b squared is. Well, it's ax minus b transpose times ax minus b. Expand that out into terms, and it's this expression. So the least squares problem can be thought of as minimize over x, the vector ax transposed times itself, plus 2 times b transpose times ax plus b transpose b. And that's the expression we're going to focus on. How would we choose x to minimize that expression? In order to pursue that, we have to first do a little more matrix algebra, extending the matrix vector operation, which we learned about in the last module.